So hello, everyone. Thank you again for joining us for today's webinar. We appreciate you taking the time to be here. My name is Davis Bowling. I'm from Radiant Vision Systems. And through Radiant, I've worked with several leading manufacturers within the AR, VR, consumer electronics, and other spaces to provide solutions for optical design and inspection to ensure the performance of these type of devices. Radiant Vision Systems specializes broadly in imaging for light and color measurement, and we've been designing and manufacturing scientific-grade automated measurement solutions for 30 years. We provide these solutions to support our global customer base, and today I'm happy to share some of our expertise within the optical testing arena and to give you a look at what it is that we develop specifically for XR devices. So today's presentation will cover XR devices. We'll take a look at their unique optical characteristics and components, trends in the XR optical design, and the performance indicators of each component. We'll talk about how to address challenges with measurement solutions, focusing on which tools provide the most effective data at each stage. Throughout the discussion, we'll give examples from Radiant's portfolio of XR test solutions and software, and then finally we'll wrap up with a summary and a Q&A. So to get started, let's take a look at today's XR devices. A lot is happening in this industry, so it's worth doing a quick review to get our bearings. The term XR is helpful for summarizing this technology broken down into virtual, mixed, and augmented reality. Here are a few of the latest and soon to be released headsets. Obviously, extended reality devices have diversified in a big way over a short period of time. Headsets are using a variety of components to serve up visual experiences differently for different use cases. When we look at the optical design of these devices, there are some common fundamental elements. A light generating element, which we would generally call a display, light directing elements, typically lenses and or light guides, and then sensors. Here we have an example of the components within a VR headset. Lenses and displays are in the middle, while sensors for depth of field and controller tracking join in the periphery. Here's an MR example. The display in this case is a laser projector and a waveguide component. And again, there are sensors to track user head as well as eye positions. XR devices combine these fundamental components within the same basic visualization constraints. One, view things close up. Two, view them across potentially wide angular fields of view. And three, to view them in a headset. As we move through this presentation, we'll see how these commonalities of XR design guide many of our approaches to measuring and ensuring the performance of devices and components, and how they have pushed us to develop new measurement tools that specifically address these constraints. Ultimately, our goal at Radiant within test and measurement is to support the goal of optical design, evaluate the performance of every optical component and the combined optical design to ensure high quality near-eye visual experiences for the user. So let's dig into it. Looking at how design is pushing limits, creating new challenges in quality control, and how measurement tools can help achieve optical performance goals. With the component landscape as diverse as an XR headset, the approach to testing is not a one and done. Testing at each layer can catch and address performance issues where they occur. We'll start at the component stage where we isolate the display, the lens, the light guide, and sensors to test their unique qualities, making sure only the best components make it into the final design. Then we test the design in whole, measuring the visual experience the components come together to create. We not only do this in the design phase, but also tolerances are set. We apply testing in production to ensure every headset offers the visual experience that the design was intended for. One of the trends that sets the biggest challenges in XR optical design is form factor. Almost universally, devices are getting smaller, lighter, more streamlined, and more intuitive. Form factor pushes every aspect of the optical design down an increasingly narrow road so that engineers are developing creative approaches to do more with less. One area is in the display, the primary driver of the visual experience. The XR display is meant to dissolve the line between virtual and reality. To do this, displays are being developed to produce visuals that more closely match the scope and acuity of human vision. One aspect of human vision that is emulated is field of view. Human vision generally covers 120 degrees binocular with a maximum field of view limit of 220 degrees. In XR design, this field of view can create immersive experiences without any perceivable limitations. Design also aims to emulate human visual acuity, which is measured in arc minutes. The smallest discernible detail in this eye chart is 1 arc minute wide for someone with perfect 20/20 vision. And an arc minute is equal to about 1/60th of 1 degree in angular vision. With this being the case, human eye resolution in XR displays is generally accepted as 60 pixels per degree, or PPD. This is also referred to as retinal resolution. As we can see from these device examples, the trend in XR displays is for larger field of view and higher PPD. Designs are also trending toward new micropixel technologies that allow more pixels per degree in the same display area, and tracking is incorporating more and more IR-based sensing components. As for field of view, while it's trending up, it's notable that AR and MR remains less than half the scope of VR field of views. So here's a visual example. VR headsets almost encompass the full field of view of binocular vision, and there are a handful of VR devices on the market that meet or exceed this range. AR and MR, on the other hand, are much narrower, at least for these devices here. More or less, this is a good reference for the state of field of view in XR. The state of resolution in XR is guided fundamentally by the display technology. As we saw in the comparison table, display tech is shifting to emissive OLED, microLED, and microLED. The smaller pixel pitches made possible by these technologies, they're attractive for reaching that human visual acuity of 60 ppd. In these examples, this shift takes displays from 10 or more micron pixel pitch in LCD down to 3 micron pixel pitch in this microLED. For reflective or projection display modules, generally LCOS has smaller pixel pitch, which is derived from the native resolution of its CMOS chip, while DLP derives its resolution from the number of its reflective micromirrors. The characteristics of each display and the parameters of the optical design guide a manufacturer's considerations for display measurement. In general, when we measure the display, either directly or projected, we're quantifying the same basic qualities. The most common are brightness, color, and also their uniformity. These need to be measured precisely to guide design improvements. Then we look for defects like dead pixels or lines, light leakage, non-uniform areas like Nura. And we can also evaluate qualities like image sticking and the visual changes over view angle. Because the goal is to measure any visual elements as seen by a user, the ideal measurement equipment will be designed to emulate human vision. Imaging photometers and colorimeters are key metrology instruments because they combine photosensitivity to brightness and color that emulates human vision. Extremely high resolution, like that of the human eye, and of course imaging, which allows us to measure the entire visible area seen by the user. Photometric imagers capture measurements of visible qualities by quantifying light, in essence, counting photons received on the camera's image sensor. Light entering the camera is filtered using the optical filters, and the camera is calibrated with a system response matching CIE functions. CIE functions describe the standard visual response of the human eye in its perception of light and color. Using these systems, manufacturers can quickly evaluate an entire visible area of display, measuring the photometric values and detecting visual defects. On the right, here's an example of our equipment, a radiant imaging photometer, and a measurement image in our software. We're showing in false color scale how we are distinguishing the values of luminance at each display pixel, as well as detecting a defective dark or dead pixel at the display edge. The optical filters of these systems separate them from standard vision cameras. On the left here, we have a radiant imaging colorimeter. This looks a little different than the camera on the last slide because this system has additional optical filters that are specifically designed for measuring color. The color filter wheel shown inside is called a tri-stimulus filter because filters correspond to the 3 CIE color matching functions shown in the graph on the right. These functions describe standard human visual sensitivity to visible wavelengths of light. During measurement, different exposures are provided for each color filter, and the calibrated camera's response emulates the CIE curve response. On the graph, the Radiant camera's out-of-the-box system response is illustrated by the dotted lines, which follow very closely with the human visual sensitivity curves illustrated by the solid lines. This describes the measurement system's accuracy for quantifying light and color values the way they are seen by a human user. As for resolution, since it's getting higher in XR displays, there's a demand for high-resolution measurement systems. The resolution of an image-based measurement system, like any camera, is defined by the pixels on its internal image sensor. In most cases for measurement, we look to maximize the number of image sensor pixels applied to the display to get more detail. A very high-resolution system is needed to apply enough sensor pixels to measure individual display pixels as shown here. At Radiant, we offer imaging resolutions up to 61 megapixels. This sounds like a lot, and it is, but the important thing to keep in mind for measurements like this is the ratio between the display and the camera's resolution. If measuring a pixel is important, we can maximize the resolution of our measurement system by focusing in on a section of the display at a time to see pixels and subpixels in detail. A microscope lens applies an imager's full sensor resolution to a smaller area of the display. This greatly increases the number of sensor pixels per display pixel. Engineers can use this for high precision measurement of individual emissive elements and for characterizing subpixel patterns, or even evaluating single emitters like a microLED. These examples show Radiant analysis software true test with a few measurement images captured by a microscope lens. In this case, we're isolating a single LED emitter to measure brightness and the luminance uniformity or fall off across the emitter. While a microscope provides a lot of detail, most display measurements in the XR testing will require imaging the full display at once. Capturing the display in just one image makes it quick and easy to compare values across the display and to detect defects. But capturing the whole display at once means applying our image sensor pixels across a larger area. So this limits how much detail we can get at each display pixel. Here's an example using two different camera resolutions, a 45 megapixel and a 61 megapixel to measure the display resolution of the microLED display within the Vario VR3. Applying the camera's resolution to image the whole display area, the 45 megapixel system would apply 2.8 by 2.8 pixels, or just under 8 total sensor pixels to measure one display pixel. And it's bumped up by a few square pixels when we take that image up to the 61 megapixel system. Why does maximizing resolution at the display pixel matter anyway? Well, generally, the industry is tending towards smaller pixels and pixel pitches, which are offered by emissive OLED, microLED, and microLED displays. Because emissive displays pixels are self-illuminating, they offer advantages for brightness, contrast, and efficiency. However, there are some downsides. Emissive displays also suffer from uniformity issues because each pixel responds differently to different current levels. Here are a couple of examples from microLED and OLED. So we want to maximize measurement resolution at each display pixel to quantify these variations and calculate correction factors. In other words, how much input needs to be adjusted at each pixel to achieve uniform output across the display. Non-uniformity in a display is called Mura, so the process of pixel level measurement and correction is called demura because it removes non-uniformity. Here on the left, we show an example of how we define or register the pixel and then measure it based on the area of the imaging sensor pixels inside the registration area. Only fractions of each image sensor pixel are used to calculate the measurement. For this reason, Radiant patented this as what we call the fractional pixel measurement method. We apply this method for demura to measure each pixel across each bright state of the display. This is illustrated by the graph to the right, where we're using measured pixel values to calculate discrepancies in uniformity and applying correction to each pixel to get uniform levels of brightness. A robust demura solution is needed to correct emissive display uniformity. Radiant's patented methods are listed here, which have been proven to provide the most accurate measurement at the pixel level to ensure viable demura processes. All of these methods rely on high-resolution imaging using systems calibrated to human spectral response. This ensures the most accurate luminance and chromaticity measurements. On the right, here's an example of how Radiant's measurement methods have been applied to correct a micro-LED display. Clearly, the difference between before and after would be noticeable when viewed within an XR device. So let's shift from resolution and look at field of view. We know XR displays are visualized in angular space with field of views that emulate the scope of human vision in some cases. If we want to emulate the human visual experience with our measurement system, and binocular human vision covers about 120 degrees, it's important that our measurement system can do the same. The simplest answer is to use wide field of view optics for this type of measurement. But there's a challenge in the way XR displays are visualized. This is from a near eye position inside of a headset. If we use a standard lens aperture for measurement, this lens aperture is located inside the lens as shown here, we're unable to capture the full field of view of the display without occlusion by the headset hardware. Think of this like looking through a knot hole in a fence. We can't see much when our pupil is far from the opening, but when we put our eye closer, we can see a wider field of view beyond the fence. So beyond matching human binocular field of views, our measurement system also needs to replicate the pupil position of the user within the headset, meaning we need to put the measurement lens aperture where the eye would be. A front-located aperture allows us to do this. So when we apply this aperture position with wide field of view optics, we can now measure the same field of view that the user sees. Radiant offers a few wide field of view lens solutions designed with this aperture position specifically for XR display testing. Lens options capture up to 120 degrees horizontal field of view, covering the area of the human binocular vision. Lenses are developed to pair with any Radiant imaging colorimeter or photometer with resolutions up to 61 megapixels. Covering this field of view with this resolution, we can capture nearly 80 ppd, which is beyond standard human visual acuity and ppd of today's VR displays. And here's an example of an image that Radiant's wide field of view lens captured from the pupil position inside of a headset. You can see from the red markings that the field of view we are measuring is in degrees. And in this example, we're measuring distortion of the projected image using a dot grid capturing plus minus 60 degrees horizontal or 120 degrees in total. We've talked about measuring pixels on the display module, but what about when the display is projected? So for this, we need to look at measuring pixels in angular space and maximize our measurement PPD. If we take our 61 megapixel measurement system as an example, we get 80 ppd across the maximum human binocular field of view of 120 degrees. And if we reduce that field of view down to 76 degrees, as covered by Radiant's latest XR lens, for example, we get as much as 126 ppd across the display. Reducing the field of view can greatly increase measurement precision when needed. Because AR and MR devices typically have smaller field of views, manufacturers can apply this advantage to test AR and MR displays with the ultimate of accuracy. In these software examples, we're applying a reduced measurement field of view to image the projected display. Excuse me, if we look at the red lines in the left image, we can see we're measuring just about plus minus 38 degrees horizontal, around 76 degrees total. In the right image, as we zoom in on a projected element, we can see we're getting pretty high resolution over the measurement image in this reduced area. Optimizing resolution in an XR design can apply the same concept of minimizing field of view for higher PPD where needed. An example of this is FOVEATED or multifocal rendering. The basis of the concept is that the visual acuity of the human eye is highest in the fovea region, which is only about 10 degrees field of view. If the highest resolution is only needed across 10 degrees, achieving 60 ppd in this area would only require a 1K display. This can reduce the cost and, of course, the size of the display component. Foveated rendering is applied in different ways. In one method, two display sources could be combined to produce an image with higher resolution in the fovea region and lower res in the peripheral region, as shown in this animation from Vario. There's a microdisplay on the bottom that is projecting a high resolution overlay onto our lower resolution display using a combiner. Other methods use lenses to vary the optical paths. For instance, in this left image where a foveated lens is used to create pincushion distortion of the displayed image, creating the appearance of a high resolution in the focus region. For foveated and multifocal rendering, we need to address two challenges in the measurement. One, different displays, and two, different focal distances. In cases where two displays are used in the headset, basically we need to measure both. Dual display testing requires that we coordinate test images across both screens so that the measurement system can capture the resulting composite image just as a human user would view it through the headset. In this solution, we can interface between the measurement system and the XR device to control both displays independently. Analysis software can facilitate side-by-side or composite analysis to look at the properties of each display and their effects on foveated visualization. To account for focus again, the measurement system should respond like the human eye. Like the eye, an imaging system's focal point can adjust to meet the depth of perceived virtual objects. However, images projected at two or more focal point demands more from the measurement system's optics than just a fixed focus lens. Radiant has chosen to apply electronic lenses for our systems, which are controlled by software to optimize focus and aperture settings for precise imaging depths. Using electronic focus, Radiant's latest XR lenses enables designers to quickly adjust to new depths within a particular scene to ensure image clarity or accurate MTF. In an automation routine, electronic lenses can be adjusted in sync with projected test images as part of a test sequence. Electronic lenses reduce risks associated with manual lenses when regular focal adjustments are needed. Imprecise lens settings increase measurement errors. For instance, out-of-focus images may obscure a pixel defect within the display. Focus also has a significant impact on MTF measurements, such as see-through MTF. If we take the software animation on the right as an example, a measurement of the sharpness of this illuminated yellow edge would be completely incorrect based on an out-of-focus image. So we can see how the edge becomes blurry when we don't have a proper focus. Electronic focus is critical for capturing projections at variable depths, especially where tolerances are so precise. Following the light's path from the display towards the eye, we reach the lenses and light guides. Waveguides enable see-through AR and MR device designs in a variety of compact form factors. The waveguide layer can have different geometrical structures, including reflective, polarized, diffractive, and holographic. The physical properties that help guide the light in these cases could be prisms, mirror arrays, or gratings, and even metasurfaces, all taking a range of unique forms. Light guided through an optical component is always impacted in some way by the physical properties of the component. By the time light from the waveguide reaches our eye, it's already bounced many times through the optical structure. This has an impact on optical efficiency, meaning light energy is reduced as it travels from the source display to our eye. The results can be poor brightness, contrast, and clarity perceived in the virtual image. This is especially important to control in these see-through designs where superimposed images must be visible in a range of ambient lighting conditions. Diffractive waveguides are more prone to issue with color tones and grayscale images shown here on the left. And on the right, a study presents the effects of incident angles of reflection on resulting MTF. Waveguides can be tested by projecting light through a light source or picture, generating unit and evaluating the resulting image. Example data on the left here shows the effects of changing the number of holographic images produced and recorded using gratings in the waveguide. As light is diffracted and combined, the color uniformity increases, but the overall efficiency decreases. Brightness, color, uniformity, and sharpness should be evaluated using a colorimetric image system to obtain absolute values to guide the optical design. These values include luminance and chromaticity and how they change across the image to determine uniformity as shown in the upper right image. Because measurement data is quantifiable, numerical values can be used to compare results based on different structural changes to the waveguide. Like waveguides, recent advances in metasurfaces have yielded ultra-thin, lightweight, flat metalenses for XR headsets. Metalenses apply these 3D nanostructures to change the polarization, intensity, phase, and direction of incoming light waves. These waves can be focused by these structures into almost any form. In AR, metalenses sit in front of the eye with the display in the metalens focal plane. Light from the display is focused onto the retina by the metalens, forming the virtual image, which is overlaid onto the scene viewed through the glasses. While metalenses have design advantages, they also have lower optical efficiency than traditional lenses. Like waveguides, this is observed as reduced brightness, contrast, and clarity. Not to mention, it's difficult to place nanoscale structures on such small components. Imprecise metalens fabrication can cause chromatic and wave aberration, shown in the image here on the left, and reduced focus performance, shown in the image on the right. This is observed as poor intensity distribution, color uniformity, and low clarity. Testing for MTF can tell us how optical components are performing in terms of transmission and reflection of light, and how this affects the perceived sharpness of the final image. 3 MTF tests methods we apply at Radiant are: 1, slanted edge contrast. This measures the ratio between black and white areas of a slanted edge. The line pair method, this measures similar values between closely spaced vertical and horizontal lines, as shown to the right, and directly measuring the line spread function, or LSF. Here's an example of the data we're going to get from an MTF test. The first graph in the upper left is the edge spread function. This shows the optical fidelity of the projected image based on a high contrast edge. The optimal clarity would produce the sharpest drop between high and low values, and showing the contrast at the edge. The derivative of the ESF produces the upper right graph, which is the line spread function, or LSF. This shows the intensity over the contrasting edge. The bottom graph here is an MTF chart based on line pairs. The x-axis shows the location of the line pairs per degree, and the y-axis shows the contrast resolution, or MTF calculation. Perfect clarity would look like a single horizontal line across the top row at a value of 1 MTF. In other words, perfect clarity across the angular field of view. So MTF can be used to analyze the imaging quality of waveguides or metalenses. A microscope can be useful in this case, especially since metalenses are incredibly small. To isolate measurements to the metalens, the component can be illuminated using an LED light source. The imaging system can then capture the output image. In the sample data, we can see how the intensity and MTF of different wavelengths are impacted by the metalens properties. The upper right chart gives the lowest MTF for the red wavelength, meaning virtual images in red will be less sharp. And again, measuring this with quantifiable data, we can guide improvements in design. As a note, although high resolution is desirable for an XR test system, there are factors to consider. An MTF measurement by a high-res camera can unintentionally resolve the display pixels, measuring contrast between the pixel separation and thus impacting the final MTF result. Shown here, the LSF of the slanted edge MTF calculation is confused by the pixelation of the display that the camera sees as contrasting elements. Note the pixelation plotted in the LSF chart to the left and the false MTF peak that results in the chart to the right. Radiant has incorporated a new line spread method within our XR test suite to account for this issue. So instead of displaying an edge for slant edge MTF, a discrete line of illuminated pixels is shown. Here we are directly measuring the LSF or line spread function by characterizing the transition of the line, and we can get a more accurate result that is not affected by the pixel spacing captured within the high-res image. So let's jump into optical systems here for a moment to touch on another important element of the XR design: the tracking and sensor technologies that are enabled by near-infrared light within the headset. Near-infrared light is one of the predominant signals used for sensing in XR. NIR, or near-infrared wavelengths, are above the visible spectrum, so they are not distracting when cast into a user's field of view. Near-sensing systems function by receiving a signal from the environment. Light is cast by a source and illuminates an area for an IR camera to see the environment. When pulsed or cast in dot patterns, near light can be used to determine object depth as well as curvature. Sensing applications rely on either LED or laser light sources to produce near IR emissions. Both types of sources can be used to enable object detection, identification, and tracking. Tracking has a range of applications in XR. An eye tracking system detects the movement of the user's gaze as well as pupil dilation to adjust visual elements within the headset accordingly. This is done by integrating near-infrared LEDs around the eyepieces of the headset, like these LEDs for the Magic Leap 1 and HoloLens 2 on the left. Eye tracking can be used to improve visualization through foveated rendering. We saw the example on the right earlier where optics are adjusted in response to the eye's rotation. And the example within the middle is software-driven foveated rendering from NVIDIA, where pixel processing and shading in the virtual image is adapted to the changing area of focus. Hand and controller tracking can be enabled by near-infrared LEDs as well. In these examples of the Oculus Quest and the Quest 2, near-infrared LEDs at multiple points on the headset cast invisible light onto the user's hands. Controllers in the left image have near-infrared LEDs integrated into them to enable relative positioning between the headset and hand movements. In controller-free hand tracking on the right, the system can recognize specific gestures for UI control. Near-infrared LEDs and lasers used in sensing applications must be measured like any light source to ensure that they provide adequate and accurate illumination. Sources are measured for radiant intensity to ensure the light that they emit is powerful enough to be detected by IR cameras. Sufficient signal is needed from the light bouncing off of targets, objects, to distinguish them from the background, just like sufficient visible light is needed to capture an object in a photograph. Near-infrared light source performance is also determined by the integrity of the light distribution. Understanding the hotspots and uniformity of a distribution can tell us whether the light is directed appropriately or if there are any trouble areas. The same is true whether we're casting a uniform beam of light or dot patterns from a diffracted laser. Since light is emitted in angular space, measurement of the angular distribution is needed to evaluate the source's performance. The solution requires an imaging radiometer. This measures light power rather than light the way it is perceived by a human eye. And as usual, there is a software analysis component. There are three methods generally used to measure light source distributions. First is goniometers. Goniometers capture the complete output of a light source in three-dimensional space. They do this by rotating an imager and a source relative to one another, measuring light distributions at every angle. This method offers the most complete data, and it's great for modeling, but it can take hours and requires bulky equipment, so it's not necessarily practical for production inspections. Light can also be cast on a wall or a screen to measure the reflection or irradiance with an imaging radiometer. This method offers a limited angular field of view and does not measure the direct radiant intensity of a source, but can be used for a pass-fail pattern match, especially for laser dot patterns. And lastly, a Fourier optic lens or conoscopic lens can capture the direct angular radiant intensity of a light source without the time, the cost, and equipment for complete rotational measurement. This solution provides a good balance of speed and data for production testing. In case some background is needed, Fourier optics capture a directional distribution of light rays emanating from a single point and then transform them to a lateral distribution. This allows the connected imaging system to image the entire visible cone of angular light rays on a single focal plane, which is its internal image sensor. In software, the image from a Fourier optic measurement system looks like the polar plot here on the right. And from this image, we can evaluate radiant intensity across the distribution and apply specific parameters, like looking at the primary emission area, called a full width half max. This is where we would measure the area of greatest intensity emitted by the source. Tolerances can be set to ensure our light source's full width half max always meets, but does not exceed a particular intensity range. Diffracted lasers can also be evaluated by Fourier optics, and we have some additional tools at our disposal here. In this image, Radiant's TrueTest NIRI software has automatically identified each emission point as a region of interest, which it will then use to output the radiant intensity, as well as the location of each dot within the XY space and by angular inclination and azimuth. If any part of the pattern is incorrect, for instance, a missing or misplaced dot, the software can then return a failed result. And this can be done while evaluating and outputting data across tens of thousands of points at once. For our last discussion, let's step out of the component level and look at how form factor in particular guides our measurement of visual elements through the headset. As everything comes together, optical test and measurement remains focused, evaluating the visual elements as seen by the user, close up with an angular field of view, and constrained to the form factor of the headset hardware. There are different considerations based on the configuration. Looking at these Vario headsets, at least we know that our measurement solution must account for the fact that there is a head strap on the top and on the back. We've already looked at measurement solutions that use an aperture at the front to enable measurement from the eye position in the headset. But what if the straps get in the way? Camera and lens are usually long, straight, and not human-headed shaped. If we still want to get our lens aperture to this position, we need to approach the display from a different angle. Angle is the operative word here. Using a folded lens design like this, we can fit our measurement system's aperture at the same near-eye pupil position without interference from the headset hardware. The basic principle is that a fold mirror inside the lens directs the light from the display to our imaging system's sensor 90 degrees perpendicular. We still use wide field of view optics, so we're still able to capture the complete view of the projected display from a near eye position. And additionally, both Radiant's fold and non-fold lens designs offer electronic focus for imaging at any perceived distance. We've talked a lot about emulating the human visual experience in XR testing, and so far we've only discussed one lens. But of course we have two eyes, and each with a slightly different perspective of a near-eye display. Based on either fold or non-folded configurations, Radiant can provide a dual eye measurement solution wherein two lenses are fit within the same headset to measure right eye and left eye at once. If needed, we can configure our measurement software's pattern generator to push test images to two different displays, like we did with the FOVEATED dual display measurement. Or in the case of a single display, we can simply capture two perspectives of the same test image pushed to a single display. At the same time, two imaging systems can acquire measurement images, and the software can perform evaluations, facilitating side-by-side analysis of left and right eye field of views. We can also perform differential measurements of left versus right eye images to ensure these images are equivalent, or any discrepancies in brightness, color, contrast, clarity, or other factors are calculated. Measuring in the headset can be done in the lab or during production. Mass production of XR devices is still evolving. Most optical designs are still so varied that lab and benchtop testing equipment remains the staple. In a recent video tour of their production facility, Vuzix provided a look at its benchtop display test station. In this middle image, you can see two of Radiant's Prometric I-Series imaging colorimeters in the back, integrated with our AR/VR lenses for in-headset inspection. Manufacturers looking to gain a competitive edge in product yield and availability are exploring more streamlined manufacturing operations. These highly automated production settings would require equally efficient test and inspection equipment. Generally, for in-headset XR display inspection, a solution would be configurable for a range of inline integrations and interface well with robots and manufacturing control systems. Here we show a rudimentary example based on automated actuators. This configuration could be adopted for dual eye measurement and a number of test criteria. Because the imaging system measures the entire visual field of view at once, and we can automate a full test sequence. A complete in-headset evaluation can be done in only a matter of seconds. The optical system is, of course, just a small part of the overall manufacturing engine. In order to provide information for other processes, the test system needs to be integrated in some way. Central to the test system automation and communication is the software. Radiant's TrueTest AR/VR software is shown in the middle here. Not only does this software apply analysis functions to evaluate measurement images, but it features API to talk to all kinds of equipment. The software pushes test images to the headset and synchronizes measurement functions on the camera. In production, these functions may be further synchronized with test fixtures and robotic positioning. Receiving data back from the camera, the software calculates the measurements and evaluates images against defined pass and fail parameters. All data is then output to the central manufacturing control system, and commands are reported out to other operations. This network requires plenty of expertise, but Radiant's measurement solutions are geared to support production testing. Test pattern generation, headset display control, camera function, and test processes are all run using automation within Radiant's TrueTest AR/VR software. Beyond this, the software supports a range of programming languages using a built-in API. So to wrap up, I want to summarize the measurement challenges and tools we discussed so you can take this with you as you consider optical testing on the road ahead. Again, a complete XR testing solution is not one and done. At each stage, from component to headset, measurement tools can help ensure tool performance. Radiant has provided display module test solutions to the consumer electronics industry for decades. Our fundamental TrueTest platform was built around the key measurement criteria for these components. Following the evolution of technology from LCD to microLED, the resolution of our imaging colorimeters and photometers has increased, and our measurement methods have become more advanced for tackling challenges like pixel level measurement and correction. As we test optical modules, we can apply the same fundamental imaging systems and software to ensure accurate brightness, color, uniformity, and MTF. Imaging systems can be paired with microscope optics for evaluating extremely small features and field of views. Tracking and sensor technology has unique criteria for ensuring the distribution and radiant intensity of near IR LEDs, as well as lasers. Radiant offers a specific test solution for these components, combining radiometric imaging, Fourier optics, and light source measurement software with advantages for evaluating polar plots and structured light dot patterns. As these components all come together, lens configurations with front positioned aperture allow us to measure the complete visual field of view from the human eye position inside the headset. A unique TrueTest AR/VR software analysis platform combines tests developed around customer XR applications and is geared towards scientific measurement and evaluation in immersive angular space and variable projection depths. Finally, production requires automation, integration ease, and flexible hardware options to meet a range of the manufacturing criteria. While fold lens optics with electronic lens control help us visualize the XR projection from any angle or space, even measuring the view from two eyes at once, software with pattern generation, API device control, and automated test sequencing provide the ultimate automated test solution for inline and end-of-line testing. To summarize, there are plenty of optical components and architectures out there in the XR space with a range of applications, but also a singular goal: provide high-quality, near-eye virtual experiences. To help manufacturers meet this goal, optical test solutions need to be able to address the performance of each component and the holistic optical design. Most importantly, measurement solutions need to be able to act as the human eye in these cases, seeing what the user sees and evaluating it with objective, quantifiable data. Radiant offers a suite of XR optical test equipment, pairing our scientific imaging photometers and colorimeters with specialized software and lens designs. These designs that equip manufacturers with the tools they need for every job. Measuring all XR components from display to lens to light guide to near infrared tracking. Evaluated in the headset, measuring the entire field of view from the human eye position, even accounting for both left and right eye positions at once. And finally, supporting rapid, fully automated testing to improve efficiency and ease from design to production. So that's our presentation. Thanks again for your time and attention. And we're going to move into the Q&A now. But if you need to sign off, and if you have any questions, please reach out to us at the email here or visit our website at radiantvisionsystems.com. Thank you.
Thank you very much, Davis. That was great. And yeah, thank you everyone for your attention. We do have about a couple minutes before the end of the hour here, but if this Q&A goes a couple minutes past and you miss anything, you will be able to access this recording, and you can send us questions as well to webinar@photonics.com. So Davis, I want to start with, is there a recommended software for testing each component in the XR design?
Yeah, okay, so yeah, that's a good question. So Radiant provides a standard platform of software that we call TrueTest. Many standard versions of TrueTest exist. We have a whole slew of recipes available, if you will. Within the XR space or the AR/VR space, we have created what we call TrueTest AR/VR. And it's a suite of test and measurement algorithms that we refer to, again, as TrueTest AR/VR. So we also offer, customer-specific TrueTest versions, and these include a variety of algorithms that we've either created for the standard display space or even new algorithms that we've created for customer-specific applications within the AR/VR XR space.
All right, thank you. What is the smallest display size and pixel pitch that can be measured?
Oh, okay, this is a depends answer. It really depends on what the user is hoping to accomplish or what it is that they're hoping to measure. What optics we're using, what the field of view is that we're looking at. So once we understand kind of the details of it, so field of view, working distance, what their resolution requirements are, all of those kinds of things, then it becomes a whole lot easier to kind of answer this questions. So we've solved several applications within the microLED space, if this gives you some kind of indication. So we look at things, kind of at 0.7 millimeters or even lower than that. Yeah. Tough to answer that one specifically without kind of knowing all the kind of parameters around what it is that they want to solve for.
Mm-hmm. How many imaging pixels are recommended to measure a single display pixel?
Okay. So also kind of in a depends answer. So it depends on what we want to measure. But as an example, let's say we want to do correction coefficients, do something like a Demura, something like this. Ideally, in a perfect world, we'd like to have like 9 camera pixels, so 9 of our colorimeter or photometer pixels to 1 display pixel. That's ideal. Now, that doesn't always happen, right? So lots of times we maybe only get a 2x2 array, so 4 of our pixels, something like this. But again, kind of depending on, do they just want to see, is it turned on or off, so black and white, or do they want to pick up some level like, some gray level at 20 versus some gray level at 23? So that also kind of plays into it. I think if this user has this particular question, we'd be happy to take this offline and kind of get into the details of their project or what they're trying to measure for, and then we can kind of make the right recommendation.
All right, thank you very much. I'm going to take a few more here before we close.
Yeah, if I can just say one more thing around
Sure,
that.
Go ahead.
We patented a technology that we call spaced pixels, and the idea behind it was, especially when we patented it, was many years ago before we got into 45 megapixels or even 61 megapixels. But the idea was we could increase the resolution, or the, let's say, effective resolution of our camera by doing a spaced pixel pattern, such that we can turn on the first pixel, turn off the next 2 pixels, and then turn on the 4th pixel, and go through this spaced pixel pattern, and basically it can double, triple, or even more the kind of effective resolution of our camera when we do that. So that's kind of another, so the idea is we're not really limited necessarily by the hardware so much, because we can do a lot of things within software as well.
All right. How is the resolution of the measurement system determined? For example, is the camera chosen by the display pixel size, pixel per degree, field of view, or other factors? And can you explain?
Okay, sorry, I'm trying to read the question. Okay, so typically we're going to start with what the measurements are that are required, just kind of like what I was talking about before. Once we kind of understand what those measurements are, then we move to the resolution of the display in both pixel space as well as potentially field of view in degrees or an XY space. And then with that information, we can dial into the appropriate lensing and camera equipment.
Are different camera resolutions needed to measure high and low resolution areas of the foveated display?
Okay, sorry, can you repeat that again?
Yeah, are different camera resolutions needed to measure high and low resolution areas of the foveated display?
I see, okay. So, yeah, okay. So I think likely in this case, we would solve for the highest resolution display, meaning that if we're looking at the 10 degrees area and that's the higher resolution display, we would kind of specify the appropriate resolution colorimeter or photometer to solve for that problem. And then of course, it's certainly going to be enough to solve for the lower resolution display that would be out on the sides, if that makes sense.
All right, thanks. I'm going to ask you two more, I think, and then we'll close. So,
Okay.
are there any limitations to the focus distance for the electronic lens?
Are there any limitations to the focus distance for the electronics lens? Yeah, okay. So generally, I want to say the answer is no. For our electronic focusing lenses, including our new XR lenses that are electronically focused, the basically infinity is kind of the focus distance. So there's some kind of minimum working distance potentially for each one of these lenses, but from the maximum working distance, it's really infinity.
All right, my last question for now is how does the measurement system account for distortion in the wide angular field of view?
Yeah, okay, that's a great question. So, one of the things that we believe at Radiant we do really, really well, and it kind of separates us out within the space, is our calibrations. So Radiant has created a whole lot of IP around our calibrations for our lenses and our cameras. And we do several calibrations in production for our lenses that are going to compensate for that distortion that can come from any of our lens offerings. And of course, kind of in this XR space or AR VR space, because we're using these wide field of view lenses, it's even more important to be able to compensate for that.
All right, that's all my questions for now. Thank you everyone for asking your questions and for leaving your comments. And I'd like to thank you all for participating. This has been Novel Solutions for XR Optical Testing, Displays, Waveguides, Near IR, and Beyond. This webinar is presented to you by Radiant Vision Systems and hosted by us at Photonics Media. And again, you've just heard from Davis Bowling, who is Sales Manager for North America at Radiant Vision Systems. Thank you so much.